Section 10.1, Parametric Equations, and hopefully this is mostly a review from the parametric equations that you studied in your pre-calculus courses. But let's just go over a quick overview. What are parametric equations before we head into the next section, 10.2, where we actually talk about the calculus of parametric equations. So if we are working with functions, what we have been used to working with in Calc 1 and Calc 2 are functions that could actually be explicitly defined or written as a function of x or y. So for instance, f of x equals, a parabola, 2x squared minus 7x plus 3, or f of x is a trig function, sine of x, or possibly oriented the other direction. So g of y is a parabola, y squared minus 1. So we have mostly been working with functions that can be written as either y as a function of x or x as a function of y. But even if we just consider for a second just like the basic circle equation, that is not really all that nice to write as an explicit function of x or y. We have to actually take a square root and break it up into two different functions, and then depending on what we're trying to do with that circle equation, work with one of those two roots. So what could we do? Well, let's talk about just in general, kind of the overview of parametric equations. So just for some motivation, right? Like we'll start with the circle. Like even if you just had a circle, or if you had something, possibly a graph that had a shape that crossed over on itself, something like this. So this is in the xy plane. Both of these are in the xy plane. Or possibly we want to talk about an object or a bug or whatever it might be. Possibly we want to talk about a pathway that is taken through the xy plane in such a way that it loops over on itself and has what we call direction. So what if I had something that looks like this and it even has direction? Like we want to talk about traversing on this pathway through the xy plane in a specific direction. We call that the direction of motion. And on this particular one, we've indicated it with arrows. Indicated on the graph with arrows. So how do we capture this without having to like break each of these curves up into little pieces? Because in order to talk about them as actual functions of x or y, we'd have to break them up into piecewise functions, look at each piece on certain intervals, and in order to get that direction of motion, we'd have to add in a third part, a parameter. So what do? Well, we're a little bit limited with what we can do with explicit definitions. So let's talk about what a parametric equation is. So a parametric equations are where we actually introduce a parameter, and then we can define x and y as functions of that parameter. So we define x as a function of the parameter, and then we define y as another function of the parameter, g of t. And we call t, we're using t here, but we can actually define the parameter with another variable if we prefer, but t is the parameter. Sometimes we use theta if we're thinking of the parameter as an angle. Here, in its standard definition, t tends to be used because a lot of times t represents a time. Like we're trying to express, like the example I have up here at the top of the screen, we're trying to express maybe how a pathway is traversed, or where an object is on a pathway at a specific time. And so t tends to be a nice variable to use. So t is the parameter. And as t varies, the ordered pairs x, y, which are themselves functions of the parameter, so f of t and g of t, trace out what is called the parametric curve. And so, for instance, like if I look at this little particular graph that I have here, once we have a parameter, then we actually get what is called, say, this direction of motion. So possibly at t equals 1 second, maybe, the object or whatever we're looking at is here in the pathway, and then over here at t equals 2 seconds, and up here at t equals 3 seconds. And we could figure out what those corresponding ordered pairs are at those specific points, okay, for the parameter. So we'll have the parameter that is defining ordered pairs that then trace out the curve. And this can be a really nice way to graph curves or graphs in the XY plane that have those characteristics that make them maybe not as easy to use explicit definitions for. So that's a very brief overview of parametric equations. And now let's get into the nitty-gritty of actually working with them and graphing them, and then into the next section where we can actually do things like calculus with them and think about how do I, if I have a definition in parametric form, how do I find tangent lines? How do I find arc length? How do I do all those things that we did with explicit functions? And so here is the official definition here. I'll just capture it on the screen again. Suppose x and y are given in terms of a third variable we call the parameter, and then the ordered pairs trace out the curve. All right, so I want to do a brief overview here of just how do we actually graph parametric curves, and then I want to just go spend the majority of the time in this video just actually graphing a couple. And so we basically have three ways to graph parametric curves. One of them is by plotting points. You know, anytime we come across a new function, a new curve, a new definition of something we want a graphical representation for, plotting points is a good fallback. So we can always start by plotting points. We just pick values of the parameter, and then we create a table, and we pick values for the parameter, plug them into both f of t and g of t, and figure out what the corresponding xy ordered pairs are so that we can graph them. Okay. All right. So that is really nice way to get started, and we'll do that for the first one. But it has its limitations and can be time consuming. So, of course, there's also the option of using some technology to either plot points or just to graph, and I will show that as well in this video. So another way to do it, and it's just basically a little bit more sophisticated way to graph points, is if we would actually just graph the two parametric equations and use the graphs to determine what the xy coordinates are. Basically that's just a visual, more sophisticated way to have a table of points plotted. And then probably the way that we, if possible, probably the way that we'll rely on a little bit more is this one, the eliminate the parameter and actually write an equation or a relationship between, so determine what the relationship is between x and y. So determine the relationship between x and y, if possible. Okay, sometimes that's not possible, but if it's possible, it's a nice way to do. Come up with the explicit definition of the curve. So the problem with that, though, is that we do lose a little bit of data. We lose the parameter, so we lose things like the direction of motion, which I defined when we were talking about those first couple of graphs. So the direction of motion is just the direction of the curve as the parametric, as the parameter increases. So the direction of the curve that is traced out by the ordered pairs as the parameter t increases. All right, so we're going to explore all three of those options, but I just wanted to talk about how those are three ways to graph parametric equations. So we'll start with the first one. So if we have this particular example, so x is defined as t plus t squared, and y is defined as 2t minus 1. And if I wanted to, so one option is to just plot points. So let's just do it. So if we wanted to plot points, we're going to create a little chart. It's going to end up with 3 columns because we have t, and then we have x, and then which is t plus t squared, and then we have y, which is 2t minus 1. And so if we're going to plot points, right, we want to have a variety of points, and if we need more, if we don't feel like we're getting a good enough graph, then we can always add more points in. But we'll start with, I don't know, let's go -2, -1, 0, 1, 2, and kind of leave it at that and see how we do. So see if that gives us enough. So if I plug in -2 into x, so if I plug -2 into x, -2 plus 4, I'm going to get 2. And if I plug -2 into y, I'm going to get -5, -4 minus 1. And if I plug in -1, I'm going to get 0 and -3. If I plug in 0, I'm going to get 0 and -1. And if I plug in 1, I'm going to get 2 and 1. And if I plug in 2, I'm going to get 6 and 3. Okay, I ran through that pretty quickly just to get us the ordered pairs. But we now have ordered pairs that I can actually graph. Now something kind of interesting happens right here, and we'll talk about that once we get it into the graph. So now I can take each of these and I can just go plot them into the XY plane. So now we go into the XY plane and we plot these as ordered pairs. So 2, -5, 0, -3, 0, -1, 2, 1, and 6, 3. So let's go ahead and get those plotted. And I'm going to pause the video and just get all those plotted and come back. Okay, so now that we have all of those plotted, we can talk about what's actually happening here. And I actually added in the parameters. So I plotted the ordered pairs, and then I added in the parameters here in red so that we can see that this is actually starting at this bottom one, t equals -2, and then increasing up. Now something kind of interesting happens right here. We have 2 points that are right there on the y-axis. And so as I'm looking at those, I'm kind of seeing this graph and I'm thinking to myself, it kind of looks like a parabola, but there's this weird little like straight line that would happen right here if I just connected those. And so what that makes me think about is maybe we should consider something in between t equals -1 and t equals 0. So I would maybe come back over to my chart, and that's what we're going to do when we plot points, right? If we see something where it looks like we might have lost some data because I just picked kind of some random t values here, maybe I need to pick another t value, something like maybe something between 0 and -1. So maybe I pick negative, so I come back here and maybe I pick -1/2. And when I plug in -1/2, I get -1/4. I'm going to squeeze it in here. -1/4 and -2. And so I get an ordered pair that is -1/4, -2. And notice what that does. So I would have the ordered pair -1/4 and -2. And that puts a point right here for t equals -1/2. And that's exactly what I was suspecting, was that we might have had a point that we were missing simply based on what I picked for my parameter. So I picked this particular example because I wanted to illustrate how sometimes just picking values, just plotting points for the parameter, you might lose a little bit of the data. And so just if that happens and you see something, an anomaly like that, where I saw those 2 ordered pairs stacked on top of each other, you might want to think for a second about if you could put a point in between for the parameter, does that give you a little more data about the graph? And so now we can connect this, and I would say this is definitely parabolic. And not only that, but because we also know that as t increases, this has direction of motion that goes up on this curve, and I'm guessing there's something back here as well. Okay, and we could plot points back here, points smaller than -2. And so we end up with a curve that looks something like that, and the arrows are indicating, again, arrows indicate direction of motion. And the direction of motion is the pathway that is traversed as the parameter increases. So direction of motion. Now we can do all kinds of things, like if we wanted to, we could restrict the parameter, and we could say maybe we only want to look at this from -1 to 1. And so, you know, we could, let's do like make a part A here. So if I had a restriction, on the parameter, and sometimes that happens, we might say that t is actually just going to be between -1 and 1. And if t were just between -1 and 1, let's plot that in blue, just so that we have a different color. So let's plotted in blue. So notice what would happen, since we already have this graph. If I was just between -1 and 1, then we would be looking at just the curve that would be plotted in blue. It would be just this little segment of this parabola. And that is what we would get. We would have restricted the parameter, which restricts the graph, and we would have just that little segment. Okay. All right, so one of the ways to do this is by plotting points. And I actually wanted to skip over to DESMOS here and show you guys how we could actually do this in DESMOS, because we can use technology to generate the same graph, and that is a nice way to do it too. So let's talk about how you would enter it in. I'm going to show you with DESMOS there. If you have a graphing calculator, I'm sure there are parametric modes, and you can enter in your parametric equations and get the graphs in a similar way to how I'm going to show you in DESMOS. So let's go ahead. We're going to go over to DESMOS, and I'm going to pause the video and get us there, and then I'll restart the video. Okay, so to graph parametric equations in DESMOS, what you're going to do is you're actually going to write in the ordered pair. So you're just going to write a parenthesis, and then with the ordered pair, the way the ordered pair is defined, it is defined as the parameter t have to bounce around a little bit here with the keypad, t plus t squared, and then we'll put a comma, and 2t, y was defined as 2t, so 2t minus 1. Okay. Now notice what happens. That actually started to give me my parametric equation, but we have just a tiny little segment of my parametric equation right there. And that's because, like we talked about on the notebook just a second ago, we talked about how if you have a restriction on the parameter, and notice what DESMOS did down here, it actually gave me a restriction on the parameter. It just said, okay, let's just let t run from 0 to 1. This is editable though, so of course, like right now it's just showing me that little piece where the parameter is from 0 to 1, but I can edit that and I can say, well, I want to look at it from, I mean, who knows, whatever you want to look at it from, maybe negative 10 to 10, 10. There we go. So maybe I want to look at it from negative 10 to 10, and I can do that. Okay, and we can see that parametric equation is being graphed. So it's pretty simple in DESMOS, pretty simple in most graphing calculators. You just go into the parametric mode and you find your definitions for x and y, and you define them as the parametric equations are defined. And then there's always a way to either restrict or give the set of parameters that you want to use. Okay, so that's how we can graph using DESMOS, and let's head back and talk about one other way that we could come up with the graph of the parametric equation. So another way to come up with the graph of the parametric equation is to actually eliminate the parameter and come up with the relationship between x and y. So if we wanted to do that, and sometimes that is easier to do than other times, but on this particular case, it's actually not too bad. So I notice on this one, we're going to rely a lot on algebra to do that. And so I notice on this particular one, I've got x equals t plus t squared, and y is equal to 2t minus 1. Well, on the y definition for the parameter, isolating the parameter is going to be pretty simple. So it turns out, that's our next example, I'll get to that in a second. It turns out on this one, isolating t on the y, very simple, it turns out that t is actually equal to just y plus 1 over 2. And then I can plug that back in to my definition here for x, and x is going to be equal to y plus 1 over 2 plus y plus 1 squared. Y plus 1 over 2 quantity squared. And if I go pretty quickly, I'm going to jump through that. That's y plus 1 over 2 plus y squared plus 2y plus 1 over 4. If I multiply both sides of this equation by 4, I will end up with 4x is equal to 2y plus 2 plus y squared plus 2y plus 1. Just kind of trying to simplify this and get it into a form that we can talk about for a parabola, because obviously we already know that because we've graphed by plotting points. But we can see right here that this is going to be a parabola. We see the y squared and we see the x over here. And so we can see it's going to be a sideways parabola. But this is going to be y squared plus 4y plus 3. And if I do a little bit of work here, I'm noticing here this is almost a perfect square. So if I add 1 and subtract 1, I should have maybe pulled the 3 over to the side, but just kind of running through the algebra pretty quick here, we get y squared plus 4y plus 4 minus 1. And then that turns into y plus 2, just playing with the parabolas and the completing the squared, y plus 2 minus 1, and then divide by 4, and I get x is 1/4 times y plus 2 minus 1/4, and there is my, and it's in a nice form. I mean, we had it up above, we had this version of it, but this is in a really nice form, and if I were to want to graph that, it's a great form. We can identify from that form, going back into just conic sections and parabolas, we can identify from that form that this is definitely a parabola that opens to the right. We can identify that the vertex here is actually at -2 actually negative, got to get it in the right direction here since it was a parabola in terms of y. So it's going to be negative 1/4 negative 2 for the vertex. And so if we pull that together back with what we had up here, we see that exact same graph we got by plotting points. What has been lost right here is what the direction of motion is. So when we eliminate the parameter, we do lose the direction of motion or any sort of bounds that are on the parameter. So when we do eliminate the parameter, we lose the direction of motion and any bounds that are given for the parameter. So just keep that in mind, that if you use this method, and we will often use this method of eliminating the parameter to get our graphs, just remember that you lose the direction of motion and the bounds on the parameter. So it could be possible that you might need to take a moment and go and actually plot maybe 2 points or 3 points just to get a sense of what the direction of motion is or which piece of it is actually being looked at based on the bounds on the parameter. So we'll look at another example where we'll go straight to this eliminating of the parameter, and then we can talk about how you have to sometimes go back and check a couple points. Okay, so that's the general theory and one example and a graphical explanation of using DESMOS to get these graphs of these parameters. I'll come back in another video and we'll do a couple more examples, and then we'll get into the fun stuff. We'll get into doing some calculus with these.